In this topic, we're going to be looking at the exciting world of electropotential and electrochemical cells, because it's not all as dull as it seems, and it's got some fantastic applications. We're going to be looking at electropotentials and the electrochemical series, and without this knowledge, you certainly couldn't solve the world's fuel problem. Let's have a look at a video.
As the world grapples to eliminate fossil fuels from our energy diet, electric cars have seen an incredible boom over the past few years. Last year, over 1 million electric cars were sold around the world. The number of Nissan Leafs, Teslas and other electric vehicles in circulation worldwide is now more than 3 million. And while there are many brands of electric car to choose from, there are only two choices when it comes to powering electric vehicles: fuel cells or batteries. Both produce electricity to drive electric motors, eliminating the pollution and inefficiencies of the fossil fuel-powered internal combustion engine. Both hydrogen and electricity.
More urgently, the UK plans to ban sales of diesel and petrol cars from 2030. And that means we need to develop these electric cars. Whether they're fueled by fuel cells or by batteries, it's upon us as scientists to develop these cheap sources of energy to power our transportation. So let's investigate what a battery is. A battery is a galvanic cell or a voltaic cell, and that was named after Luigi Galvani or Alessandro Volta, and it's an electrochemical cell that gets its electrical energy from spontaneous redox reactions that take place in the cell. And it's usually made out of two different metals immersed in electrolytes, or individual what we call half cells with different metals in their ions in solution connected by something called a salt bridge. In this half cell here we have a solution of copper sulfate, 1 mole per dm cubed copper sulfate. Immersed in the beaker is a piece of copper metal. In the second half cell, the solution is zinc sulfate, and the zinc ions are usually 1 mole per dm cubed, and immersed in this electrolyte is a piece of zinc metal. Joining the two half cells is what's called a salt bridge, and that's simply a piece of filter paper soaked in concentrated potassium nitrate. The circuit is completed when the two metal electrodes are joined to a high resistance voltmeter, and the high resistance voltmeter here is recording the potential difference generated between the two half cells. So the two half cells join together to make what's called an electrochemical cell, and it generates a voltage. So normally in the class I would show you this diagram of a normal electrochemical cell and get you to label the components. So what I'm going to do now is to walk you through those components, pause the video and see if you could repeat that. So let's go around the cell in a clockwise direction. First of all, the reading on the voltmeter is known as the Ecell, and Ecell, or the EMF, is the maximum voltage that can be produced by the cell. The metals immersed in the electrolytes are called the electrodes, and these are the conductors used to permit the flow of electrons and provide surfaces at which the oxidation and reduction reactions will occur. The electrode normally drawn on the right hand side is known as the cathode. So if we were to short circuit that cell, i.e. take away the high resistance voltmeter and allow electrons to flow, we would see a buildup of copper metal on this positive electrode. Electrons are flowing from the zinc, and therefore the copper ions in the beaker can pick up electrons and form copper metal. Thus, electrons have been gained and reduction is happening. So reduction happens at the cathode. A way of remembering this is red cat. For this galvanic cell to work, when we remove the high resistance voltmeter and electrons flow, the redox reaction that would occur if you were to put the zinc into a solution of copper ions must be spontaneous. So let's now have a look at the function of the salt bridge. The salt bridge here is to allow the migration of ions. So if we were to short circuit the cell, remove the high resistance voltmeter, here we would have a buildup of a negative charge as copper ions are reduced to copper metal. To balance that, therefore, we'd get a flow of positive ions from the salt bridge into the beaker, thus completing the circuit. Conversely, at the negative electrode, if oxidation is going to happen and zinc metal, you can see here, getting oxidized to zinc ions, we're going to get a buildup of positive charge. So from the salt bridge, we're going to have a flow of negative ions into the beaker to counteract that and complete the circuit. So the salt bridge allows the migration of ions to complete the electrical circuit. If the positive electrode is called the cathode, the negative electrode is called the anode, and oxidation always occurs at the anode. And finally, these electrolytes, concentration of which are 1 mole per dm cubed under standard conditions, are the species that allow oxidation and reduction reactions to take place. So, summary, what's the galvanic cell? It's a type of electrochemical cell that converts chemical energy of oxidants or oxidizing agents and reducing agents into electrical energy. A quick reminder of the difference between a galvanic cell that we've just met here and an electrolytic cell. Think about the battery in your phone. So while your phone is working, providing electricity, electrons will be flowing in this direction and you're going to get a depletion of the electrolytes. So as the anode dissolves and the cathode builds up, the potential difference between the two starts to decrease until it eventually runs to zero and your battery runs out. When you plug your phone into recharge, what happens is the flow of electrons from the plug from your charger forces the redox reaction in the opposite direction, and therefore the polarity is reversed, and you start to get a build-up or replenishment of your electrolytes as electrons are forced in the opposite direction, thus recharging your battery. So a rechargeable battery must have a redox reaction that is reversible. It will drive the non-spontaneous redox reaction, and the redox reaction that's not spontaneous is forced to take place by you pushing electrons around the circuit. So in an exam, if you were asked to draw a diagram of a cell showing both half cells, make sure that under standard conditions, so the value Ecell, remember, is the maximum voltage generated when two half cells are joined together, and this zero sign with a line through it tells you that the standard conditions are 298 Kelvin, the pressure of about 100 kilopascals, and the concentrations of the solutions must be 1 mole per dm cubed. Your salt bridge is simply drawn by a solid line there, and here we have a high resistance voltmeter, which you could just draw as a circle with a V in the middle. Make sure you can draw this diagram by pausing the video and checking your answers. When you carried out this experiment and connected the two half cells, one of the electrodes would have given a negative reading. And therefore, when you switched them round, you could tell which was the positive electrode and which was the negative electrode. And the best way of representing this is on a chart. So when we carried out this practical, we connected a variety of half cells together. How would we represent this data? Well, the best way of representing this data is to draw up a chart with the most positive electrode on the right hand side, and the most negative electrode on the left-hand side. Now, say for example, we measured the potential difference this time between a copper half cell and an iron half cell. And this time the reading on the high resistance voltmeter is plus 0.7 volts. If we now did another two half cells and connected the iron cell to a silver cell, and the voltage that was read was 1.24 volts, and we've been told that the silver electrode is positive, let's put this data on the chart and then calculate the voltage of a silver copper cell, even though we haven't connected the silver and the copper half cells together. So let's put that on the chart. So we can now use this data to calculate the value of a cell that we've not even created, because we can see here that copper is more positive, that silver is more positive than copper. And if we know the standard electrode potential for the iron copper cell, and we know the standard electrode potential for the iron silver cell, we can simply see that the difference between the iron silver and the iron copper would give us the standard electrode potential for the copper silver cell. So it's simply the difference between the two, which is 1.24 volts, take away 0.74 volts. So we can predict that if we connected a copper and silver half cells together, we would generate a voltage of 0.54 volts. Now later on, we're going to look at what happens if we dilute the electrolyte in one of the half cells. Because remember, all of these have been measured when the concentration of the electrolyte is 1 mole per dm cubed. And therefore, it's obvious that by changing the concentration of the copper ions and the silver ions, that will have an impact on the voltage. But will it increase it or will it decrease it? And that's something we're going to look at later on. What we can't keep on doing when we're describing galvanic cells is to keep drawing an illustration like this. And what we do is simplify it by using what's called a conventional representation or line diagrams. So let's look at our simple copper zinc cell here. So what we use is a conventional, what's called REDOX red. This side, the left-hand side, represents what is happening at the anode. On the right-hand side is representing what's going on at the cathode if electrons were allowed to flow. So first of all, we know that if electrons are allowed to flow at the anode, oxidation takes place. So the reduced species, which in this case is the zinc metal, would become oxidized to Zn2 plus ions. That's the oxidized species. Electrons would then flow around the circuit, and the oxidized species in this case, which is a copper, becomes reduced to copper metal. This double line here represents a phase boundary of the salt bridge, which is obviously in both beakers, so it's represented by two solid lines. So let's have a look at the conventional representation for this galvanic cell, the one that connects zinc and copper. First of all, the reduced species is zinc, and the oxidized species is Zn2+. The solid line here represents the phase boundary because we've got a solid in contact with an aqueous solution. We then have the double line here showing the salt bridge. The oxidized species on the right-hand electrode, that is the cathode, are the copper ions. The reduced species is the copper metal, again surrounded by, which is a solid, and the copper ions are aqueous, so we have a phase boundary here. Let's look at some more complicated line diagrams. In this spontaneous redox reaction, lithium is a much more reactive metal, and it would spontaneously displace nickel ions and turn them into nickel metal. We can see here that lithium is definitely the reduced species, because on the other side it becomes positively charged and it becomes oxidized. So the oxidation state of lithium here is 0 and the oxidation state of lithium here is +1. So to work out which is the oxidized species and which is the reduced species, we simply break it up into two half equations. So the first step is to break the redox reaction into two half equations. So lithium metal will become lithium ions. And therefore, to become lithium ions, to balance out the charge, we add an electron here. And therefore, we know that that is oxidation. On the other hand, nickel, which is 2+, has therefore gained electrons to form nickel metal. And we know that the oxidation state has changed from +2 to 0, and therefore we know that's a reduced reaction. So therefore, on the reactant side, nickel is reduced, lithium is in its reduced state, and nickel is in its oxidized state. So the next step is to use our redox rule. So that's read, ox, red. So let's look at again our two half reactions. Lithium here is becoming oxidized and nickel is becoming reduced. So the reduced species in our redox reaction is lithium. So we write lithium, and lithium is a solid metal. We put our phase boundary in and lithium becomes oxidized to lithium ions. That is then connected by a salt bridge, and the nickel 2+ in the reactant side is in its oxidized form, and as a product it becomes reduced. We have our phase boundaries, and this is our conventional cell diagram. Now let's just look at this. Remember that this is the anode, the negative electrode, and this, the nickel, is the cathode. Why? Because at the cathode, reduction is taking place, and at the anode, oxidation is taking place. The nickel cathode is going to be the positive electrode, and therefore the lithium is going to be the negative electrode, where oxidation is taking place. The conventional cell diagram is written from left to right because this is showing the flow of electrons. So as lithium gets converted to lithium ions, the electrons flow along and the nickel ions become nickel metal. So in your chem sheets you were asked to write the conventional representation of cells given some illustrations of how the cell would be set up in the laboratory. The first one we've done already. So pause the video, have a go at it, and then check your answers. So let's look at the first one. We can see that in the anode that the zinc, the equilibrium with the zinc, would move towards the oxidized form, and therefore it's the negative electrode. And this is the reduced form, oxidized form, reduced form. So let's look at the next beaker. Again, we've got two metals. By definition, the anode, the negative electrode, goes on the left-hand side. Well, how do we know that this is a negative electrode? Well, we know from year 9 that aluminium is a more reactive metal than lead. So the more reactive metals are better reducing agents. The equilibrium would move in this direction and aluminium ions would become oxidized to aluminium metal. Electrons would flow around the circuit and therefore the lead ions would be reduced to lead metal. So again, we have read, ox, red, and the line showing the difference between the two phases. Now in this cell here, we haven't got a metal. there is no metal on the left-hand side. We've got hydrogen gas. And on the right-hand electrode, we have dichromate ions and chromium ions. So what happens when we don't have the metal electrode involved in the redox couple? Well, when the metal isn't involved in the redox, when there is no metal in the redox couple, remember that the purpose of the electrode is simply to conduct electrons and to provide a surface for the redox reaction to take place. So what we can do is substitute a metal with a platinum electrode, because the platinum electrode will allow the flow of electrons and it will provide a surface. But because platinum is so unreactive, it doesn't take part in the reaction. It's just there to conduct electricity. So how would we represent this cell when there is no metal involved? Well, first of all, we can see from our illustration that the left-hand electrode is being represented by this half cell here, which is a hydrogen electrode. And the positive electrode, because they've told us it's positive, is this chromium dichromate redox couple. So because this is a negative electrode, it must be the reduced form, which in this case is hydrogen, because that's got an oxidation state of 0, forming hydrogen ions, which is its oxidized form. That's the negative beaker, where oxidation is taking place and the equilibrium will shift to the left. In the right-hand side, therefore, the positive electrode is where reduction is going to take place, and this is where our oxidizing agent dichromate will pick up electrons and get reduced to chromium-3 ions and water. So let's show the representation of that half electrode. First of all, hydrogen is a gas, and hydrogen ions are aqueous. So we draw a solid line to show the difference in the phases, gas and aqueous. We don't need to write the stoichiometric ratios in the conventional representation. Now, in the other half cell joined by a salt bridge, we have dichromate, which is the oxidized form, Cr2O7 2-, and there are hydrogen ions also in there, so we separate those with a comma because they are also in the aqueous phase. So if the species are all in the same phase, we simply represent the separation with a comma. And we've also then got the reduced species, which are the chromium ions. So the hydrogen ions here, even though they're not taking part in the redox reaction, they're just dissolved in acid, appear in the conventional diagram. Again, we do not need to represent stoichiometric ratios. Now, there are no electrodes represented here, so when there is no metal in the redox couple, we represent the platinum electrode simply as PT, followed by a solid line because of the phase boundary. And on the cathode side, again, because we've got a mixture of two ions and there's no metal here, we represent the electrode by a solid line and PT for the platinum electrode on the right-hand side. So remember, this is the anode, the negative electrode, and this is the cathode, the positive electrode. So let's look at another cell where there is no metal on one side. So on this side, on the positive electrode, they've told us this has the positive polarity. Why? Because it's been drawn on the right-hand side. They've shown us the potential flow of electrons. So this is definitely going to be the cathode, because this is where reduction is going to take place. So if the high resistance voltmeter was removed, the manganate 7 ions would become manganese 2 ions, and the iron metal in this half cell would dissolve to become Fe2+. Therefore, this is the positive electrode and this is the negative electrode. So let's write over our species that this is the oxidized species becoming reduced, and this is the reduced species that is going to become oxidized. And therefore it follows, if this is the anode, we have iron, which is the reduced species. It's in a different phase to the Fe2+ ions, which are in the aqueous phase. We then have our salt bridge, and in our cathode, where reduction is taking place, we have our manganate 7 ions, aqueous. It's in an acidic medium, even though the hydrogen ions aren't involved in the redox reaction per se. They don't change oxidation state, we include them. And the manganate is reduced to Mn2+. Now there is no metal on the right hand side, and therefore we need to put our platinum electrode with a phase boundary there. In our experiment, when we made electrochemical cells, we measured the potential difference between a zinc cell, half cell, and a copper half cell, and we got a reading of plus 1.10 volts. When we measured the potential difference between an iron half cell and a copper half cell, we got a reading of 0.70 volts, where copper was always the most positive electrode. So what we were doing was referring our half cells to copper. So knowing those two values, we could have calculated the value of a zinc iron cell without actually carrying out the experiment. So we were using copper as a reference electrode. Now, in the world of chemistry, we don't choose copper as a standard electrode. What we do is we use a standard hydrogen electrode to which we can refer the voltage of all other half cells. And by definition, our standard hydrogen electrode is given a value of 0.00 volts. It's given that value by definition. And now we can compare the electrode potential of all other half cells to what's called our standard hydrogen electrode. The reason for this is historical, because more reactive metals, for example lithium metal, if you were to put lithium metal in an acid in a solution of hydrogen ions, the lithium would displace the hydrogen ions and form hydrogen gas, and the lithium would dissolve. A more reactive metal, therefore, a less reactive metal like copper will not displace hydrogen ions from an acid, and therefore we can see that copper is to the right of the hydrogen electrode. So hydrogen electrodes are chosen as the standard by which we compare the oxidizing or reducing ability of all other redox couples. So let's take a closer look at the standard hydrogen electrode. So let's look more closely at the standard hydrogen electrode. The standard hydrogen electrode, if we look at the left-hand side of this diagram here, has hydrogen gas being pumped in at 100 kilopascals. The hydrogen gas goes in through a simple glass tube over a platinum electrode. And the platinum electrode provides an interface between the hydrogen ions, which are at a concentration of 1 mole per dm cubed, and provides electrons so that the hydrogen gas can exist in an equilibrium with the reduced form, which is the hydrogen gas, and the oxidized form, which is the hydrogen ions. So as I mentioned, the hydrogen ions have to be at a concentration of 1.0 moles per dm cubed. This then is connected via our salt bridge to your other half cell, and when the other half cell is connected with a high resistance voltmeter here, the Ecell, or the EMF which is generated, is equal to something which we call the standard electrode potential. And the standard electrode potential is given the symbol E with a zero with a line through it. The zero with a line through it represents the fact it's carried out under standard conditions. So in this case, we have a chlorine half cell connected to our standard hydrogen electrode. And chlorine gas, again, is pumped in at 298 and at 100 kilopascals pressure into a solution of chloride ions. And the chloride ions have a concentration of 1.0 moles per dm cubed. So what is red is something called the standard electrode potential, So what is the definition of standard electropotential? Well, let's say that again. Standard electropotential is the electromotive force generated when a half cell is connected to a standard hydrogen electrode under standard conditions. So the standard conditions are all gases at 100 kilopascals, concentrations of solutions at 1 mole per dm cubed, and a temperature of 298 Kelvin. Now clearly this diagram, you wouldn't be able to represent this diagram under exam conditions. So let's look at more conventional representations of the standard hydrogen electrode. So the standard hydrogen electrode is sometimes referred to quite simply as SHE, standard hydrogen electrode. So as mentioned before, the standard hydrogen electrode, or SHE, is the reference half cell for electropotentials. So you'd start off firstly by simply drawing a beaker with a straight line, no wavy lines, there is no wind in there. Inside the beaker is a solution containing 1 mole per dm cubed H plus ions. So if you're using sulfuric acid, you'd be using a concentration of 0.5 moles per dm cubed sulfuric acid, because remember, sulfuric acid is a dibasic acid and dissociates into twice as many moles of hydrogen ions. So if you're given 0.5 molar sulfuric acid, that would give you a 1 molar solution of the hydrogen ions. So next you would represent the platinum electrode, which is dipped into your acid solution. So that's your electrode for providing a surface for redox to occur and for the flow of electrons. Now you would draw a glass tube surrounding your wire with the platinum electrode, making sure there's a gap in it for hydrogen gas to enter. The tube must also have holes in it to let the bubbles of hydrogen gas escape. So don't seal that up, otherwise it would explode. Now you would label this area here with hydrogen gas at 298 Kelvin and 100 kilopascals pressure. Next, to complete the circuit is your salt bridge, which would be obviously your saturated potassium nitrate solution to complete the circuit. So the equilibrium, which is set up in that half cell before it's connected to anything, is you would have your oxidized species, which are hydrogen ions, on the left hand side, and the reduced species as the hydrogen gas on the right hand side with its equilibrium. So by definition, we assign this half cell a voltage of 0.0 volts. The half equation, or the conventional representation for this half cell, is platinum, your reduced species, which is hydrogen gas, followed by your phase boundary, because that's aqueous, and a gas as a solid line here. And by convention, the hydrogen electrode is always written on the left hand side. So let's look at an exam question and let's revisit the definition of what a standard electropotential is. So when any electrode system is connected to a standard hydrogen electrode under standard conditions, the potential difference, or the electromotive force, is called the standard electrode potential, and remember it has the symbol E0 with a line through it. So this was an exam question which said that in a test, aqueous iron 3 ions are reduced to aqueous iron 2 ions by iodide ions. This reaction could be used to provide electrical energy in a cell. The standard electropotential for the reduction of Fe3 plus ions into Fe2 plus ions, so that's Fe3 plus ions into Fe2 plus ions, can be measured by connecting a suitable electrode to a standard hydrogen electrode. Draw a clearly labelled diagram to show the components and reagents, including the concentrations in the iron 3, iron 2, and do not draw the salt bridge or the standard hydrogen electrode. So lots of students went and drew a whole cell with the standard hydrogen electrode. Let's just have a look at what this half cell would look like. So quite simply, in your beaker you would need a platinum electrode. Lots of students drew an iron electrode. But think about it, the redox system is to measure the potential difference when an iron 3 and an iron 2 redox couple are measured in equilibrium. There is no iron metal, and therefore we do not put iron metal, we must use a platinum electrode. Inside the beaker is a mixture of Fe3 plus ions, Aq, and Fe2 plus ions, and both at a concentration of 1.0 moles per dm cubed. It says do not draw the salt bridge or the standard hydrogen electrode. In the next part of this exam question, it says a salt bridge is used to complete the cell, and this could be prepared using potassium nitrate solution and filter paper. State the purpose of the salt bridge and state one essential requirement of the soluble ionic compound used to make the salt bridge. So remember, the purpose of the salt bridge is to complete the circuit by balancing the ionic charge. Now remember, potassium nitrate contains what I usually refer to as spectator ions. They do not take part in the chemical reaction. So that's the answer. The requirement of the ionic compound is it. So I'll state that again. The components of the salt bridge must not react with either of the electrolytes or take part in the redox reaction. So potassium nitrate is good because these tend to be spectator ions. They don't form insoluble salts. This next question unusually places our hydrogen electrode on the right hand side, which is very unusual. If we were measuring the standard electrode potential by convention, it's written on the left hand side. So let's just answer this easy part. So remember, it says the aluminium is rubbed with sandpaper, and we do this with all our metal electrodes because aluminium tends to have an impervious, insoluble aluminium oxide layer. So it's to remove the aluminium oxide layer. Now it says draw a label diagram of suitable apparatus for the right hand electrode. So here they're asking us to draw how would you draw a diagram for a gas in equilibrium with its ions. So how would you sketch this quickly? And I'm going to do this freehand. You would simply draw your beaker in 2 dimensions. You would then draw a glass tube going into the beaker with a hole in it to allow the gas to go in. Remember then there is a wire which connects that to your platinum electrode, which you would label. The hydrogen gas would go into the beaker, and the pressure of the hydrogen gas is at 100 kilopascals, and the temperature is equal to 298 K. Now remember, inside the beaker you would have hydrogen ions, and it doesn't say which reagents, so your hydrogen ions in there would be at a concentration of 1.0 moles per dm cubed. Before we move on, let's look at a stretchy question that came from the November 2020 examination series. So it talks about the difficulty ensuring consistency with the setup of a standard hydrogen electrode. So instead, we're comparing our electrode to a copper, and this is being used as what is called a secondary standard. So the first part is asking you to design an experiment to measure the standard electrode potential of this titanium oxide redox couple, instead of using hydrogen, using the copper 2 plus copper redox couple. The main gist of it was how would you make up a standard solution. So this is linked to another video that I've produced, and I'm going to put the link below. The part I want to focus on here is how to connect the electrodes and how the measurements should be used to calculate the standard electrode potential for this titanium oxide titanium electrode. And at this point I'm going to focus on that part. So from the exam question, we've been told that the titanium electrode is negative. And therefore, first of all, I've written out the balanced equation for the titanium 4 oxide ions being reduced to titanium metal. So this is the oxidized form and this is reduced form. And therefore in this beaker here, we're going to have a titanium electrode. So we can simply draw the titanium electrode as a wire made out of titanium. You don't need to do anything artistic here, and we can then label that as titanium metal. Now we've already previously described how to make these titanium 4 ions in solution, and therefore in that beaker there we're going to have titanium 4 oxide aqueous ions, and we're also going to have some acid as well. We've already made it up in acidic solution. Now what happens is we're going to put our reference electrode, and our reference electrode is copper metal. So inside this beaker here we're going to have a strip of copper metal, and the copper metal will therefore be in a solution of copper ions which are in the beaker here. So copper ions in this beaker here, Cu2+, and our copper ions must be at a concentration of 1 mole per dm cubed. Similarly, we've already described how to make up a 1 molar solution of our titanium 4 ions. Then we must connect the circuit externally with a high resistance voltmeter, and then we must add our salt bridge. So to draw our salt bridge, simply a line, and line, and let's now label that our salt bridge. And we know that our salt bridge is made up of filter paper soaked in saturated potassium nitrate solution. The next thing would be to construct our chart with the most positive electrode, and we have been told that our copper 2+ copper redox couple, when compared to a standard hydrogen electrode, is plus 0.34 volts. We also now, once we've completed the circuit, measure the standard electromotive force, or the EMF, or the Ecell of our apparatus. And that Ecell would give us this value here. So that is the Ecell when we connect the titanium oxide, copper electrode. And that would give us the Ecell value there, and that is the reading that we'd get on our voltmeter. And now we can find this value here, which would be the standard electrode potential for the titanium 4 oxide titanium metal value. So this would give us the standard electrode potential for titanium 4 oxide titanium, even though we don't have a standard hydrogen electrode. How can we do this? Well, from the diagram we can see that Ecell, for our diagram above there, is equal to the sum of the standard electrode potential for the titanium half cell here, added to the standard electrode potential of our copper redox couple. We have this value, and therefore if we rearrange this equation, the standard electrode potential for our titanium half cell is equal to Ecell that we've just measured, take away the standard electrode potential for our copper 2+ copper half cell. So why would we use a reference electrode? So our copper electrode here will have been standardised and sent to the lab against a standard hydrogen electrode. But since this is more stable, it's much easier to compare the standard to measure the electromotive force, or Ecell, when you join together your titanium electrode to a copper electrode than it is to join a titanium electrode to a standard hydrogen electrode. So in this case, the copper electrode is known as a secondary standard electrode. So let's just reiterate that again. You would measure the value of the EMF by connecting your half cell to your secondary standard. In this case, that's the copper electrode. We already know the standard electrode potential of our secondary standard. And then you would connect these two. You would get the E cell against your unknown half cell and the secondary standard. And then you would use this equation saying that E cell is the sum of the electrode potential for the secondary for your unknown added to the standard electrode potential of your secondary standard. On page 12 of your independent study booklets, you are now given a table of standard electrode potentials. Now they're usually arranged in order, starting with the most negative. So we can see at the top that the lithium half cell here has a standard electrode potential of minus 3.03 volts. This tells us a lot. This tells us that this equilibrium lies massively on this side to the left, and it favours the oxidised form. Therefore, standard electrode potentials can also be thought of as standard reduction potentials. The more negative the standard reduction potential, the less likely the species is to exist in its reduced form. So the reduced form is always written on the right hand side, and the oxidized species is always written on the left hand side. Now, as we go down the table, you can see that the standard electrode potential becomes less negative. As you move down, the more powerful oxidizing agents start to appear on the left hand side. So if we look here, we have vanadium 5 oxide being reduced to vanadium 4 oxide, and the electrode potential for that is now positive. So the more positive the value, the more likely the equilibrium shifts in the forward direction, and the more likely it is that the species will exist in its reduced form. We know that silver is a precious metal that doesn't really tarnish or become oxidized. And we can see that because it has a positive reduction potential. Ag plus is more likely to gain electrons and become reduced to silver metal. Right at the bottom of the table is fluorine gas. And we know that fluorine gas is one of the most powerful oxidizing agents we know. So it's really important to remember that on the on the right hand side, you will always find your reducing agents on the reducing agent side or the right hand side. Your oxidizing agents you will always find on the left hand side. The more positive the value of the redox couple, the more powerful an oxidizing agent is, because the equilibrium will tend to move in the forward direction and become reduced. So as you go up the table, the reducing power increases on the right hand side. As you go down the table on the left hand side, the oxidizing power increases. So our more powerful oxidizing agents are found to the bottom of the table with the more positive reduction or standard electrode potentials or E0 values. So the more positive, the more powerful a reducing agent. Data. And we would find the value for the standard electrode potential, first of all, for So now what we're going to look at is how to calculate the value for Ecell. So that's the reading on the high resistance voltmeter here when two half electrodes are combined. And what we need to know is the values from the standard electropotential data. So what would be the reading on this voltmeter here if this half electrode here, which is the anode, is connected to the more positive electrode, the manganate one here, which is the cathode? Well, what we would do is we'd go to our table of standard electrode potential. The iron 2 plus for the iron metal getting oxidized to iron 2, and we'd find out the standard electrode potential for this reaction here. At this point it's careful to check because there are two redox reactions involving Fe2+. But the one where iron and metal is equilibrium with Fe2 plus ions is minus 0.44 volts. And for the manganate 7 manganese 2 redox couple, the value is plus 1.51 volts. So there from our data table of standard electrode potentials. To calculate Ecell, the equation is the value of the standard electrode potential of the right-hand electrode, subtract the standard electrode potential of the left-hand electrode. By convention, the left-hand electrode here is the more negative electrode, which is the anode, and the right-hand electrode is the more positive electrode, which in this case is the cathode. So Ecell is equal to plus 1.51 take away a minus 0.44 volts. So in this case, the reading that we get on the voltmeter is plus 1.95 volts. And that tells us that the redox reaction would be spontaneous. That is, if you were to mix MnO4 minus ions together with Fe metal, you would get a chemical reaction in which the manganate was reduced to Mn2 plus and the iron got oxidized to Fe2 plus. And that is our spontaneous cell reaction. So let's have a look at some of the questions you got from your chem sheets. So let's look at the first example, the nickel tin. So first of all, on this is the left-hand side, and this is the right-hand side. So for A, Ecell is the standard electrode potential for nickel, and therefore, for the right-hand side, minus the standard electrode potential for the left-hand side. So the right-hand electrode is the tin 4 tin 2 couple, which is this one here, which has a value of plus 0.15 volts. We now take that away from the left-hand side, and that's the nickel 2 plus redox couple, which is here, and that has a value of minus 0.25 volts. So we calculate that to give us a value of plus 0.4 volts. Let's do B. So the silver electrode, the silver iron redox couple is plus 0.8 volts. And the left-hand electrode, the iodine iodide redox couple, is plus 0.54 volts. To calculate Ecell, Z right man, that gives us a value of 0.26 volts. Finally, let's have a look at redox couple Ecell for C. And this time it's the standard electrode potential for the bromine bromide redox couple, which is here, which is plus 1.07. Take away the value of the chlorine redox couple, which is here, which is 1.36 volts. Now this time we get a negative value. Ecell is negative, and that tells us that reaction is not spontaneous. That redox reaction is not spontaneous. That tells us that when we mix chloride ions with bromine, the chloride ions cannot be converted to chlorine and the bromine cannot be converted to bromine. Well, we know this from group 7 last year, that bromine isn't a powerful enough oxidizing agent to take electrons off chloride ions, and therefore that redox reaction won't happen. So this tells us the value of Ecell, whether the redox reaction is spontaneous or not. And a negative value tells us that the redox reaction will not take place. In these examples, we're being asked to find an unknown standard electrode potential. So in this cell, the magnesium and titanium cell here, we've been given the standard electrode potential of the magnesium half cell, we've been given the value of Ecell, and therefore we can find this unknown here. So again, let's write over the top. This is the left-hand electrode and this is the right-hand electrode. So for A, if we write out the equation, Ecell equals the standard electrode potential of the right-hand electrode minus the standard electrode potential of the left-hand electrode. But we are missing the value of the right-hand electrode. So if we rearrange this equation, the standard electrode potential of the right-hand electrode is equal to Ecell added to the standard electrode potential of the left-hand electrode. And therefore Ecell is 2.00 and the magnesium electrode is minus 2.38. And when we add those together, that will give us the value of the titanium 3 plus titanium 2 plus half electrode. And that gives a value of minus 0.38 volts. You can check the answers to the rest of them in your chem sheets. What we're going to do now is apply those standard electrode potentials, or what we call the electrochemical series, and we're going to use them to predict whether a reaction will take place or the direction of the spontaneous redox reaction. So first of all, in this question 1, it says write an equation for the reaction that would take place if this zinc redox couple and this nickel redox couple are connected together, and then explain why this reaction takes place. Well, first of all, we can see that the zinc is the more negative electrode, and therefore that is going to be placed on the left-hand side, and the nickel electrode is going to be placed on the right-hand side. And because nickel has got the more positive standard electrode potential, or more positive reduction potential, the nickel ions will get reduced to nickel metal, because we know at the right-hand electrode reduction takes place. At the left-hand electrode, because zinc is the more negative electrode, the equilibrium will shift over in this direction and the zinc metal will become oxidized. So if we were to write out an equation for that reaction, nickel is behaving as the oxidizing agent because it's getting reduced, and the zinc's behaving as a reducing agent because it's giving up electrons. Because electrons balance out, we can now add the two half equations together. In this case, because there are the same number of electrons on both sides, remember they should cancel out. So the nickel reacts with the zinc displaces the less reactive metal from the solution, and nickel metal is produced. So to explain this, we can say that this reaction takes place because the nickel redox couple, that's this here, has a more positive standard electrode potential than the zinc redox couple. Could we summarise that? So here's a way to summarise this in an exam. Because the Ni2 plus Ni redox couple has a greater standard electrode potential value than the Zn2 plus Zn couple. It's conventional when you're writing a redox couple to put the oxidized species first and then the reduced species on this side. So it's almost the same as the equation, leaving out the electrons. And this is the standard answer for explaining why a reaction may or may not be spontaneous. So question 2 is, what reaction would take place if a piece of silver and copper was placed in a solution containing a mixture of silver nitrate and copper sulfate? Justify this using the electropotential below. So again, let's compare the two reactions. This time, our silver has a more positive standard electropotential than the copper redox couple, and therefore silver ions are going to get reduced to silver metal, and therefore copper metal would get oxidized to copper ions. So now we can write a chemical equation for the reaction. First of all, write an equation for the two half equations. So here we can see that silver is becoming reduced, and we can see that copper has become oxidized. So what we do now, before we can add the two half equations together, we need to balance for electrons. So the reducing agent here, the silver ions that are gaining electrons, we need to times by 2 to form 2 moles of the electrons. So now if we put in two of these, and we're forming 2 silvers. Now we can cancel out electrons on both sides, and the overall equation for the reaction is that 2 moles of silver ions are reacting with 1 mole of copper metal to produce 1 mole of 2 moles of silver atoms and 1 mole of copper 2+ ions. Now if you ask what you would observe, you can see quite clearly that the copper metal here would start to dissolve. This would start to corrode away as it reacts to form copper ions. And you would then also see a deposit of silver on the silver metal as the silver ions in solution start to form silver metal. So if you're asked about observations, think logically what you would see. The copper metal dissolves to form blue copper solution, so the solution would become even more blue, and the silver ions, which are colourless, would start to form a silver deposit on the piece of silver metal. So calculate the value for Ecell for this spontaneous reaction. Remember, Ecell equals E right minus E left. So the electromotive force, or Ecell, the reading that you would get if the two half cells were connected. The right hand one is the more positive electrode, which is the silver, because that is where reduction is taking place, and the left hand electrode is where oxidation is taking place, and that is 0.34 volts. The spontaneous reaction, naturally we're going to get positive Ecell value, which is 0.46 volts. So how would we write this? How would we justify this? So whenever you're asked to justify this, you use the concept of standard electropotentials and redox couples. So here we can say that the standard electropotential of the silver ion silver redox couple, when you write out a redox couple, you always put the oxidized form there and the reduced form here, is greater than the standard electropotential of the copper 2+ copper redox couple, and therefore silver plus ions get reduced. Now we could ask the question, will hydrogen ions oxidize sodium metal to sodium ions?
A chunk of sodium in sulfuric acid. Okay, 3, 2, 1. Whoa!
So clearly that reaction is spontaneous. Let's write two half equations and then use standard electropotentials to justify why that reaction is spontaneous. Here we can see that the standard electropotential of the hydrogen ion hydrogen gas redox couple is more positive, or is greater than, the standard electropotential of the sodium ion sodium metal redox couple, and therefore the hydrogen ions will get reduced to hydrogen gas, and the sodium metal certainly will get oxidized to sodium ions, and as we saw, the reaction was pretty violent. Now Let's write that justification down in words. So again, justification in words. The standard electropotential of the hydrogen ion hydrogen gas redox couple is greater than the standard electropotential of the sodium ion sodium redox couple, so the sodium ions become oxidized. Pause the video and see if you can write an overall equation for this reaction. So again, we write up the two half equations. The reducing agent is only giving up 1 electron, so we need 2 moles of the reducing agent. And therefore that will now give up 2 electrons. We can cancel the electrons on both sides. So the overall equation for the reaction is 2 moles of sodium metal reacting with 2 moles of hydrogen ions form 1 mole of hydrogen gas and 2 moles of sodium ions. Now we're going to look at a A-level exam question. And normally in the exam questions you are given a list of standard electropotential data, and usually the standard electropotential data is running from the most negative all the way down to the most positive. So in this question it says use the standard electropotential data to answer the following questions. And remember, each of these can be reversed under suitable conditions, because remember this is redox equilibria. So in this experiment we've got an excess of potassium manganate 7, and that's being added to a solution containing vanadium 2+ ions. It asks you to determine the vanadium species present in the solution at the end of this reaction. State the oxidation state of vanadium in this species and write a half equation for its formation from vanadium 2+. So what we do is we need to identify the species from its name. So potassium manganate contains MnO4- ions, and we know that potassium manganate ions, or MnO4- ions, are purple. So what I'm going to do is to underline our manganate ions here. They're reacting with vanadium 2+ ions, and we identify our vanadium 2+ ions in the chart there. So now it says determine the vanadium species at the end of the reaction. So what you've got to realise here, that there is unlimited amounts of our manganate 7 ions. Remember, the potassium ions are spectator ions, they're not taking part in the reaction, so we can ignore them. Well, we can certainly see, looking at the standard electropotential data, that manganate ions would certainly be reduced to manganese 2 ions, and the vanadium 2 ions would certainly get oxidized to vanadium 3 ions, because the standard electropotential of the manganate redox couple is much greater than the vanadium 2+ vanadium 3+ redox couple. But don't be kidded into thinking it stops there, because we can see that this is the reduced form and this is the oxidized form, and therefore that is an oxidizing agent. But we can also see that down here we've got vanadium 3+ that can act as a reducing agent. It's on the reducing agent side, and still the redox couple, the manganate redox couple, still has a more positive reduction potential or standard electropotential than the vanadium 3+ redox couple, and therefore more of our MnO4-, more of our manganate will get reduced to manganese 2, and this time reduced, and this time our vanadium 3+ will get oxidized to this species here. Now if we work out the oxidation state of vanadium in VO2+, oxygen is -2, the overall charge on the ion is +2, and therefore it follows that vanadium would have a +4 oxidation state. So more manganate 7 gets reduced to manganese 2, and the vanadium 3 will get oxidized to vanadium 4. We can now see that vanadium 4 is also a reducing agent, and the redox couple of the vanadium 4 going to this new species here is still less positive. So this vanadium 4 species here will get oxidized to this vanadium species here. The formula of that vanadium species is VO2+. The charge of the oxygen, some of the oxidation states, is equal to the charge on the iron, and therefore the vanadium here has an oxidation state of +5. So vanadium 4 gets oxidized to vanadium 5. So it follows that the final species at the end of the reaction is this VO2+, and the oxidation state of the final species is +5. And now it just follows to write a half equation for the formation of vanadium 5 from vanadium 2. So let's now use our usual rules. So we're forming vanadium 2+, that's dioxovanadium 5 ions, 5 because of the oxidation state of the vanadium within that, from vanadium 2+. So we're going to use our simple basic rules. And remember that if you've got oxygen appearing on one side of the half equation, that is water on the other side. So therefore we're going to have 2 moles of oxygen molecules on this side because we've got 2 oxygen atoms. And then the next rule is if you've got hydrogen in your water on one side, it forms hydrogen ions on the other side. So that means we now need 4H plus ions on this side. We're now balanced for atoms, and now we simply need to check the charges. Well, over on this side, the overall charge on all of the species is +2. And on this side, we've got 4H pluses and a plus there, and therefore the overall charge on this side is +5. We need to add electrons to the more negative, so the more positive side, and therefore this is the more positive side, and therefore to balance the charge we need to add 3 electrons, and that now means that the overall charge on both sides is +2. Well, that makes sense because we're being reduced from the +5 oxidation state all the way down to the vanadium 2, and therefore to go from 5 to 2, the difference is we need to add 3 electrons. So there is your balanced half equation, which is 2H2O plus vanadium 2 plus AQ going to form vanadium 5, that's VO2 plus AQ, and 4H plus and 3 electrons. Let's look at our simple voltaic cell again. If the high resistance voltmeter is in place, remember no current can flow. So within the 2 beakers, within these 2 half cells, the systems are in equilibrium. And the equilibrium is between the reduced species and the oxidized species. And it can move in both directions. Now, normally, under standard conditions, the concentration of zinc ions is 1 mole per dm cubed, and the concentration of the copper ions is 1 mole per dm cubed. But let's ask what happens if we were to drop the concentration of the zinc ions. What effect would that have on the value of Ecell, the standard electrode potential? Well, we need to look here at Le Chatelier. So if we were to drop the concentration of the zinc ions in this beaker here, in order to oppose the change in equilibrium, the system would move in this direction to favour the oxidized species. Now, if the reaction is going to move in the backwards direction to favour the oxidized species, the standard electrode potential is going to become even more negative. So if it was 0.1 moles per dm cubed, the standard electrode potential for this is minus 0.76 volts. If we were to remove the zinc ions to oppose the change in equilibrium, more zinc metal will dissolve. It's going to go in the backwards direction, and therefore it's going to become even more negative. So let's have a look at that on a simple diagram. So again, if we connect these two half cells up, the distance between them on this diagram represents the standard electrode, the Ecell for that cell when you connect those two half cells. We're asking ourselves what happens if we were to decrease the concentration of the zinc ions. So if we decrease the concentration of the zinc ions, the equilibrium will move to oppose that and move in this direction, and therefore the value of Ecell is the value of the standard electrode potential for the zinc half electrode is going to get even more negative. As it becomes more negative, the equilibrium shifts in this direction, so you can now see that the difference between the two electrodes has increased, and therefore if you drop the concentration of this, the value of Ecell is going to get larger. You can see the difference between the two electrodes, potential difference, has increased. This time, let's look at a scenario where we reduce the concentration of the copper ions. If we were to reduce the concentration of the copper ions, again, the equilibrium would move in this direction, so the value would drop below 0.34 volts. The standard electrode potential of the copper redox couple would drop to smaller than 0.34 volts, and that would result in the potential difference between the two decreasing, and therefore we would say here that Ecell would drop. Let's do this conversely. If we now increase the concentration of the copper ions, if we now increase the concentration of copper ions, according to Le Chatelier, the system will oppose a change in the increase in copper ions and move in this direction. And therefore that means now that it will become greater than plus 0.34 volts, and therefore if it's greater than 0.34 volts, the standard electrode potential is going to increase, and therefore the value, the effect on Ecell is that it will increase. So these are all to do with equilibria and Le Chatelier. So at the start of the video, we were looking at how the role of the chemist to solve the world's problems. First of all, let's look at the commercial cells that we know today. So the ones that we know today, the ones that you actually recognise, these batteries here, are a really important source of electrical energy. And we've got two types of batteries. Those are rechargeable and non-rechargeable. And we've also got cells called fuel cells, and we're going to be looking at the difference between the two. Now, what is brilliant about all cells is that it's a portable source of electricity. You don't need to plug it in at the mains. So remember that a battery is actually more than one cell joined together. We made a cell in the practical, and if you join more than one cell together, that is a battery. So a car battery is usually made up from 6 cells of lead and sulfuric acid joined together. So really, a battery is actually lots of cells joined together. So the batteries that you throw away, or the non-rechargeable batteries, the chemicals get used up. And as the chemical gets used up, the electromotive force drops, and then you bin them. So as the chemicals start to deplete, the battery goes flat, the voltage drops to 0, you bin them, and therefore you have to dispose of them. Now, in this world of recycling and the chemicals that are actually used, that is quite wasteful. So what's the difference between a rechargeable battery and a non-rechargeable battery? In a non-rechargeable battery, the reaction is not reversible. The reaction is not reversible at all. So you can see in a normal battery here, you've got something like zinc and manganese, and what happens is the zinc starts to lose electrons and forms this zinc complex, and the manganese therefore gains electrons and gets reduced. And again, these are not replaceable. So what's the difference between these and rechargeable batteries? Again, here I'm giving credit to ChemSheets for these images. The rechargeable cells are usually made up from lithium, and they're called lithium-ion batteries because they contain lithium metal. Yeah, that is one of the most reactive group 1 metals, and the lithium metal is in equilibrium with lithium ions in this cobalt-4 oxide complex. So let's have a look at how you'd work out, first of all, the electromotive force of this battery, and then let's look at the overall reaction during discharge as the spontaneous reaction is taking place, and the overall reaction as it recharges. Now, for a battery or for a cell to be rechargeable, the reverse reaction must be feasible. And for the reverse reaction, we call that the electrolytic reaction. So when you plug it into the mains, the reverse reaction is forced. So let's have a look at the overall reaction during the discharge of the battery as your mobile phone is running. So let's look at the two half equations and decide which is going to be the anode and which is going to be the cathode. So remember, REDCat reduction occurs at the cathode. So this is the reduced species and this is the oxidized species. The redox couple with the more positive standard electrode potential is this one here, and therefore this is where reduction is going to take place, and therefore this is the more negative electrode, and that's where oxidation takes place. So this electrode here is the cathode with the more positive reduction or standard electrode potential. So this one is going to go forward in this direction here and become reduced, and therefore the lithium metal is forced to become oxidized. So we write out the two half equations, and this time showing the lithium metal getting oxidized and then these lithium ions here becoming reduced to form this compound with the lithium, with the cobalt ion here and oxygen. So now if we add the two half equations together, we're balanced for electrons, and therefore the lithium ions actually cancel out on both sides, and therefore we've got lithium metal reacting with the cobalt-4 oxide. The electrons cancel out and they form this compound here, LiCO2. So that is the spontaneous reaction that occurs in your lithium cell as your mobile phone is running. And if we calculate the EMF or the standard the Ecell for this reaction, it's the right hand electrode, and this is the one with the more positive standard electrode potential, take away the one with the more negative standard electrode potential, and it generates a huge potential difference of 3.60 volts. So this is what is happening as your battery in your phone or your cell discharges. Now eventually, as your mobile phone runs flat, that is because all of the lithium metal has been used up. So what we now need to do is to plug in and reverse this reaction. So the reverse reaction, quite simply, is this compound here. As you force electrons in, gets converted back to lithium metal and the cobalt-4 oxide. So you might say, well, you also get these battery cells, these little circular ones, and it's really, really dangerous if you were to swallow one of those because it's got pure lithium metal. You saw earlier in the video what happens when sodium metal reacts with acid. Can you imagine lithium metal in your stomach acid would be just as explosive? So you certainly want to keep these out of the reach of children. Here are two more familiar cells. So this cell is what's commonly called the lead acid battery in your car. It's extremely heavy if you ever tried lifting one out, and that's because of the relative atomic mass of lead. So remember, it's made up of 6 cells, and where reduction is taking place here at the cathode, you have lead-4 oxide, and that actually reacts with sulfuric acid, picks up electrons to form lead sulfate. At the same time, lead metal, which is the anode, gets oxidized to form lead-2 sulfate. Let's calculate the EMF that is generated in a single cell in your lead acid battery. So each cell in your 6-cell battery produces about 2 volts. So if you've got 6 cells joined together, the total voltage of your car battery is 12 volts. So let's have a look at the overall chemical reaction during discharge. So because this is the more positive redox couple, this reaction is going to go forward and the lead-4 is going to the lead 4 is going to get reduced to lead 2 sulfate, and this is the more negative electrode, so the lead metal here is going to get oxidized to lead 2 sulfate. So let's now write a balanced equation for that reaction. So let's write out this equation reverse. In both the reduction reaction and the oxidation reaction, we have 2 electrons involved, and therefore the electrons will cancel out. Notice also that on both sides we have lead sulfate, and therefore we're forming 2 moles of lead sulfate on this side, 2 PbSO4 and 2 H2O. Now on this side we've got 2 H plus ions, and we've got 2 H plus ions on that side, so they cancel out. So on the left hand side we have lead plus lead 4 oxide plus 2 lots of sulfuric acid, making 2 lots of lead sulfate and 2 lots of water. When you put electricity in to recharge a battery, either by the car's reversing the reaction or plugging it into a battery recharger, the reverse reaction will take place. So during charge you get a reversible reaction as you're recharging your battery, and the lead sulfate and water combine together again to give lead metal, lead 4 oxide, and sulfuric acid is regenerated. Now pause the video and look at a nickel cadmium rechargeable batteries. So in the nickel cadmium rechargeable battery, the cathode, this is where oxidation is where reduction is taking place, is nickel 3 hydroxide. You then have this separator soaked in potassium hydroxide, which will act as your salt bridge, and the anode, this is where oxidation takes place, is toxic cadmium metal. So could you calculate, using the standard electrode potential, the value of the EMF? What's the overall reaction as the battery is discharging? And when you plug it into the power source, what is the overall reaction during recharge? Do that on a piece of paper and then check your answer by pausing the video. So to calculate the EMF of a lithium nickel cadmium battery or lithium cadmium cell, it's around 1.4 volts per cell. Now, the overall reaction during discharge, as the reaction is running, that's a spontaneous reaction, because this half electrode here has got a more positive reduction potential. That's going to go forward, and the cadmium is going to go backwards and become oxidized. So let's now write out the 2 half equations by first of all reversing the anode, which is cadmium metal and hydroxide ions, forming cadmium hydroxide and 2 electrons. On the other side we've got the nickel 2 oxide plus water plus 2 electrons, forming nickel hydroxide and 2 hydroxide ions. Now again, because we've got these 2 electrons being produced as the cadmium gets oxidized, the electrons cancel out. And also we've got hydroxide ions on both sides as well, so they cancel out. So during discharge, if you add these 2 together, that will give you your overall reaction as those batteries are running down. So the forward reaction as the battery is discharging is the nickel 2 oxide reacts with the cadmium in the presence of water, forming cadmium 2 hydroxide and nickel 2 hydroxide. And therefore when it's all depleted and you plug it into the mains to recharge it, the cadmium hydroxide simply combines with the nickel hydroxide, and the reverse reaction takes place to form nickel 2 oxide, water and cadmium metal. There was a mistake here. The cathode should say NiOH brackets 2. So now we've come full circle. At the start of the video, we started to look how we could use fuel cells and the hydrogen economy to replace fossil fuels. So this little picture here is an example of a simple hydrogen oxygen fuel cell. So on one side, you've got tubes bringing hydrogen into one part and oxygen bringing them to another. Now it's really important that these compartments are separate, because if you've ever seen hydrogen and oxygen with a spark, you'd have a massive explosion. Fortunately, these two gases never come into contact. So let's have a look at the chemical reactions that are going on within that fuel cell. There are two types of fuel cell, and the diagram that's shown here is what's called a proton exchange membrane cell. Protons, because protons or hydrogen ions, are able to move between the electrolytes. And this membrane separates the two electrodes. Now the anode, the negative anode, where oxidation is taking place, is hydrogen gas is pumped in there. So you can see that hydrogen gas has electrons removed, turning it into hydrogen ions or protons. The electrons are pumped around the external part of the circuit, and it's these flow of electrons, which is a current, which can then be used to power your electrical device. Now here we have the hydrogen ions moving across the membrane. Now at the cathode, the positive electrode where oxygen gas is being pumped in, these then pick up the protons from the proton exchange membrane. Electrons are delivered from the external part of the circuit, and you get reduction taking place. So you can see that hydrogen and oxygen are going in, and therefore water in both cases is coming out. So this is called a proton exchange membrane. So that is an acidic or proton exchange membrane. You can also have an alkaline hydrogen fuel cell. So here, the negative electrode this time has hydrogen ions in an alkaline medium. But this time, instead of being turned into protons, the hydrogen gas reacts with hydroxide ions, and the hydrogen gas turns it into water and becomes oxidized. So again, it's still the anode. The electrons are pumped around the external part of the circuit, where reduction at the positive cathode, the oxygen therefore picks up the electrons, combines with water and not protons this time, to produce even more hydroxide ions. When you add these two equations together, the overall reaction is exactly the same. Hydrogen plus oxygen makes water. The cell EMF is exactly the same for both the proton exchange membrane and the alkaline hydrogen fuel cell. But notice, if you're given a set of data, make sure you're choosing the right half equation for under alkaline conditions or acidic conditions. You may have to discuss a risk-benefit analysis of using cells as opposed to fossil fuels. So we know that with fossil fuels, they are non-renewable. We're going to run out. Whereas benefits of cells is a portable source of electrical energy, which means that the chemicals are renewable. We've got infinite amounts of oxygen, we've got infinite amounts of hydrogen. So the benefits is that with rechargeable cells, what you can say is there is a much lower environmental impact. However, because there's only water being produced. But what the problem is again, this is with hydrogen fuel cells, the only waste product is water. But the risks with hydrogen fuel cells is you need a constant supply of hydrogen, and therein lies the problem. Where do you get your hydrogen from? How do you make cheap hydrogen? If anybody could make cheap hydrogen, you're going to be a billionaire. So the problem is that hydrogen is flammable, and if you mix with oxygen, it's really explosive. You have to keep those two gases apart. And the dilemma is, one way of making hydrogen is from coal. So you'll still make, or methane, so you still make using fossil fuels. And also the chemicals that are used in those exchange membrane are very, very expensive. The high cost of making those fuel cells as well. So you've also got some waste issues with those. Now let's go and look at the non-rechargeable cells. They're cheap to make. The chemicals tend to be cheap to make, but you throw them away. Where do you put those batteries when you throw them away? Rechargeable cells, because you can keep using them, there's less waste in the long run, and they're cheaper in the long run because you just keep using electricity to recharge them. And theoretically, they should have a lower environmental impact. But think about it, you've got cadmium in there, really toxic, so you've got some waste issues at the end. So you should be able to come up with a benefits risk assessment of ordinary cells, rechargeable cells, and non-rechargeable cells, and hydrogen fuel cells.